I'm very excited to be here because I literally get my visa 4 hours before my flight. Yeah, so pretty excited. And the last talk is a very decent talk for a high-level introduction on the best practices on SREs and machine learning, right? So now let's dive into some details, specifically on the AI infrastructure layer. And today I'm going to share how we involve to manage them and what we are facing these days. A little introduction about me. I started my career at Google right here back about 10 years ago as an SRE, where I learned the foundation of how we manage distributed systems. And then I moved back to China to start my career on Ant Group, where I started building my Kubernetes SRE team and to advocate for SRE's best practices. And as we all know, when ChatGPT got released in 2023, and everyone's focus now gradually shift to model trainings and large language models. Well, that's the thing, right? And so do we. Every big high-tech company try to train their own language models, and so we are facing challenges for the AI infrastructures. So the Transformers, right, the Optimus Prime comes from Cybertron to the Earth, they need to adapt, right? So do we, and the SREs. So today I'm going to share how the SRE principles can be applied to the AI infrastructures in a different way. Yeah. So the agenda for today's talk is quite straightforward. So to make sure everyone's on the same page, I'll first do some background introduction and to motivate you why we are doing this talk and why we are, what are we facing, right? So the definition of AI infrastructure is kind of interesting. Let's make this a little bit more specific. Let's say we are only tackling this issue from the model training perspective, especially for large language model training. Okay. So on the left-hand side is oversimplified distributed training architecture. You can see there's a bunch of nodes. Each node is responsible for computing part of the model's weight, right? And they need to exchange the parameters weights across different nodes through the high-speed network and do forward and backward propagation and to converge to the loss function, right? So it's oversimplified model. And I don't think I need to go any deeper here because this is not a AI 101 talk. So on the right-hand side is what I think the stack for the AI infrastructure, where everything below the model framework, I believe it's in the scope for what we are going to manage here today. We have data center, we have storage layer, where you store your data, training data, you store your model data. You have GPUs, you have networks, and all the essential management services to run all these infrastructures, right? And of course, Kubernetes, right, where everything is going to be orchestrated on. So to give you a little more detailed example, what are we facing today when we first started our model training? I think one of the biggest issue is to handle the training interruptions. Because as you can see from the bottom diagram, that was a chart back in 2023, I think. As you can see, we've encountered multiple model interruptions during the training every day, every several hours. That includes overnights, right? We have to get up 3 a.m. in the morning and to resume the training and try to see what's happening. Is there anything we can do to kick off some bad nodes so that we can continue our process? Because otherwise, we've invested so much on the GPU assets, and they are sitting there idling. That's a waste of time and also money, right? Real money. Yeah. So another thing that I didn't quite catch is that from engineering perspective, is that nowadays, when we are debugging such interruptions on the training job, it requires different level of knowledges. And as you can see, if we zoom in the diagram a little bit, on the top diagram, that's the GPU utilization ratio on a training job, like with 1,000 plus GPUs. As you can see, the curve bounced all over the place. And everyone knows that there is something wrong with it, and we would like to see a very smooth curve, right? Where you start the job and the utilization ratio will be on like a steady pace. But it turns out that if you just examine the training jobs log, the system logs, you inspect a few like node level metrics, that's not enough to tackle the issue, right? So we pull the whole team, we call it the AI task force, to actually go deeper. And finally, we find out that, okay, there's only one single GPU that's causing this problem. And the reason is that there is a bad optical module on the GPU chip. And why it's bad? Because according to the guy in the data center, they said, okay, there may be some dust when installing these GPUs. So yeah, this causes all the GPUs to perform unstably. And that's the thing we are facing these days that we never imagined before. So that was just a very quick example on how to describe what we are facing compared to the old microservice land, right? So in the microservice land, I know pretty much every day, everyone is now running their jobs on the cloud, right? Whether or not you manage your own Kubernetes or you use managed service, that doesn't matter. We all know that single point of failure on the microservice land is not that important, right? You never lost your sleep because one single node failed, because we have all kind of tools to tackle the issue. You can just kick off the node, or you do some GSLB to shift the traffic a little bit, and you have pretty much very mature tools for that. And in the microservice land, it just requires low network bandwidth most of the time, right? However, in contrast, on the GPU training land, we all see that there is a high impact on a single node failure, right? So it has a very large blast radius. It can cause like 1,000 GPUs to just hang there and doing nothing. And it's hard to go, there's a very high cost to do the recovery or to do the initialization, and maybe 10 to 15 minutes to load a very big large model, right? And as you can see, this graph is a typical GPU architecture. You don't need to understand any details there, but you just need to know that it requires very high bandwidth for network communication to exchange all the parameters. And everything happens in like millisecond unit. So that's the thing we are facing right now. So as SREs, we all know that in the classical SRE methodologies, we have 5 pillars to tackle our job, right? The reliability measurement, the automation, the observability, the incident response, and the capacity management. So what do they mean in the GPU training land? That's what I'm going to share with you today. Okay, so let's first talk about metrics, right? In the plenary talk, we all know that there are new metrics. So in this talk, let's be a little more specific. What are the new metrics for the training jobs, right? How you can measure the reliability, or what's the reliability measurement for a training job? So back then, my boss asked me this question in a room, saying, hey, you came from Google, right? Everyone talks about SLO there. So tell me how you can apply SLO philosophy to our GPU training, right? We actually debate for a while, and we conclude that the classical SLO methodologies may not that need some kind of transformation, right? So think about it, right? How do you measure the service availability for a training job, which may be across 100 nodes, right? does 99% of success really mean anything? Because if 99% of the nodes are successful, but just one node failed, your entire job is failed, right? So that gives you nothing. And so, of course, you don't have any like RPC chains in your GPU architecture, right? So there is no success ratio SLOs, no latency SLOs. So what should we do? All right. Okay, so now I prefer using the term like reliability measurement for the GPU clusters. So let's think about it, right? So here is a simplified diagram for representing different stages for a GPU training job, right? You submit the job and you enter the scheduling phase. And once you get your allocated GPU resources, then you start your job initialization and then you start iterating your training data, right, to get the model trained. And maybe you put several checkpoints there, like for every 100 steps. And then until your model got interrupted because some kind of failures. So we SREs jumped in and fixed the issue and restart the model training again and again. So we believe that, as you can see from this diagram, so we come up with actually two Northstar metrics that we think are very useful to guide our engineering effort. The first one is called training time efficiency, which is described as the ratio of effective training times compared to the total elapsed time in a training job, right? This is the measurement of the utilization ratio for your actual resource consumption, right? And another one is from the supply chain perspective, right? To measure the availability of your resource supply, like the portion of the total amount of total available GPU time related to, let's say, a theoretically maximum GPU time in a given time window. So how many GPU time is available. To use that as a target, now we can do our SRE practices to improve these numbers, right? So since our time is limited, so I just pick two topics. One is from observability, and one is from GPU management, to show you some detailed examples how we do things to manage the infrastructure. So everyone loves talking about observability, right? But today, I'm not going to talk about whether or not we should use Prometheus or use OpenTelemetry for this. Let's save that for the promcon. And I'm not going to talk about what kind of monitoring products should we use because, yeah. So instead, let's just back to the basics, take a step back, and let's tackle a very specific problem and issue using data and mathematics. So you've already seen this graph, right? So how can we use all these monitoring data to identify these degraded GPUs quickly, right? So that's the thing we actually want to do, right? That can ease our day-to-day life. So the key challenge is so you have so many data, right? We have we come up with these three challenges. I think let me explain one by one. The first is called the high cardinality. Imagine you have thousands of GPUs, and each GPU may explore hundreds of metrics, and you have hundreds of jobs, maybe across several clusters, and all the labels combinations is huge, right? And the resolution. The resolution means the frequency of scraping your data points, right? So traditionally in the microservice land, probably you scrape your data every 30 seconds or every minute. That's probably enough for you to tackle your day-to-day issue. But in the GPU land, if you want to actually see or find some subtle issue, like a sudden burst in your GPU communication or the transmission ratio, you need millisecond resolution. And that amplifies the number of data or the data total storage you need to actually store your monitoring data, right? And finally is the granularity problem. We need to preserve all the details before doing some sort of aggregation, because you never know at what level you actually need to drill down, right? from the example I just illustrated, we need to drill down to the hardware level. And so that point of data, we need to keep that. So the high cardinality and high resolution brings a problem that the metrics here are unreadable to human, right? Well, I will show you two graphs. If you think this graph is a little, is still readable, then how about this one, right? Yeah. Don't worry about the details or the actual meanings of the graph. I'll explain that later. But just get a feel, right? You don't actually want to read that data, especially at 3 a.m. in the morning, right? You wake up from the interruption, and you don't certainly want that. So let's make friends with math and statistics, right? We need some statistics tools to help us to do these automated analysis on these data, right? So we have two hypotheses here. So the first one is we call row-based uniformity, right? That means with each training steps, right? So if several nodes, they are performing the identical roles in the training, right? They should explore similar metrics, right? That's the first exam we want to test. And the second one is we call temporal consistency, is that across the training step, whether or not you are at the first step or you are at your 100th step, all the nodes should actually demonstrate similar behavior, right? It's just you are loading different data into your training model, right? So I'll introduce two weapons here, just like Optimus Prime needs to upgrade his weapon to tackle the new enemy, right? So the first weapon, is called the JS divergence, which is a statistical method which you can quantify the similarity between different probability distributions. But I'm not going to get into the details there because I'm not a good teacher. I think GPTs can do better than me in this topic. Just get a demonstration here. So on the left side is a graph, like there are 8 graphs here, right? So 8 graphs, each one represents one single GPU, and maybe it's the GPU utilization ratio for that specific GPU, that time series. We convert them to a probability distribution diagram. That's the histogram you are seeing in the middle. And then you apply the calculation based on the JS divergence, then you can get a heat map. And the heat map will show you if they behave similarly or they behave if there's any abnormal behavior. Green means everything looks similar, and if anything is red or yellow, that means there probably is something wrong. So like what the previous graph I showed here, right? So if you convert that left graph into this heat map, into this heat map, you can clearly see that there's one single GPU that's performing abnormally, right? The actual meaning of the left-hand side is the computational power of each GPUs across time. So we find that GPU may be degraded, so we kicked off that GPU and restart the training to help us to regain the iteration speed. Okay, so the second example is even more powerful, the Fourier transform, which is a powerful technique that can convert like the data from the time domain to the frequency domain, right? So on the left side, let me explain what's the meaning of the left-hand side graph. It's the RDMA transmission rate for several GPU cards at 10 millisecond resolution. So as you can see, it's kind of like unreadable. You may probably see some pattern there, but it's hard to quantify, right? But the magic happens when you transform to the frequency domain. As you can see from the frequency spectrum, you can actually see there's one single peak there. And if you see the frequency peak and convert it back to the time period, you can actually gain a very useful insight. That means, the character that's maybe too small for the backend audience. I'll explain it here. So that means if we filter out the low frequency noise and find the dominant frequency domain at the peak, this represents the regular cycle time for our training, for each training step. And then we can use that to know that once we know that what the normal rhythm should be, we can easily detect when a node failed out of sync, right? If your training is getting slower, then this frequency domain graph will change, and you'll get a longer period of time, and then you know something bad may be happening, right? All right, I know it may be a little confused to you because I think I'm down for the mass torturing here. Yeah, so let's move back to the next topic about granularity, right? So sometimes we've seen like how metrics can help us, right, to detect these type of problems. But sometimes we need more like granularity. For example, here are the diagrams. We are visualizing the execution timeline for different operations across multiple nodes. So in the model trainings, there are two main operations you need to be care of. The first one is called matrix multiplication, right? That's what GPUs are good at, to perform these multiplication quickly, right? The second one is called network synchronization, that you need to broadcast your GPU weights and or calculated data across different GPU nodes. Well, that's the two basic operations you need to be aware of. So the left-hand graph is a demonstration of a. So on the left-hand side, there is operation number 2, where you can see that it lasts longer time than other operations. That means there may be some computational bottlenecks there. So you may need to like optimize for your GPU training, right? And on the right-hand side, you can see actually the last line, the node 4, is delaying its operation on each operator, right? So that means probably this node may be bad. So we need such visualization or such granularity to actually to figure out what's actually happening, right? Otherwise, we may be optimizing for a wrong direction. So how can we get there, right? You are probably thinking that sounds like distributed tracing, right? You are absolutely right. So we have a proof of concept implementation to use CUDA programming to actually try to instrument these type of operations and get the trace data back and perform it, convert it to the trace data that Chrome browser can actually read and visualize on the left-hand side. And what you are seeing on the left is a visualization for these traces, give us a timeline view of exactly what's happening on each across multiple GPUs simultaneously. So now we can clearly see which operations are running and how long they take, and most importantly, like how they align across time. Okay, so I'm not going to get into the details of the implementation of CUDA event because that can take for like about an hour, which certainly we don't have that time. Okay, so but just to get you a sense that in the new land, right, where we need to manage GPUs, certainly we need some new weapons and new tools for us to tackle these problems, right? But I'm not saying that the traditional observability method doesn't work. It still works, like in many situations. And for that, let's move to the next topic about GPU management. So now we've explored how we like detect these anomaly nodes on our GPU clusters. And the next question is, how can we actually manage these expensive resources, right, once we identify them? So remember we talked about GPU availability, like from the measurement part, right? And it turns out it's not the only metrics we need to like pursue, especially when you are reporting to your high-level management, like your CFOs, who are asking, okay, so we've invested millions of dollars, and where is our GPUs, and how are they performed? And so what we are seeing here on the left is a Sankey diagram, or a waterfall diagram, that tracks the flow of GPU resources through various states, right? So this breakdown is crucial because GPUs are incredibly expensive asset, and they deserve babysitting, right? We need to know, like, So starting at the top, let's say, we have the total GPU inventories in-house, right? And some of them are broken and waiting to be replaced or being repaired, right? So the rest of them made their life into our Kubernetes clusters, right? But they are not immediately get to be schedulable because some of them may be cordoned off for like drivers update or for like some like load test or other issues, right? And then among all those schedulable GPUs, we can actually allocate training jobs on top of them, right? But there are still some vacant ones because of fragmentation, right? That's the one we need to optimize. And among all those allocated GPUs on the training job, some of them are actually being actively used, right, by doing GPU computations, but some of them are sitting idled because of maybe your model's framework is not optimizing the computation well. That's the thing we also want to like optimize. Okay, so I think this work, if you are reporting to your CFOs, you may use this type of diagram. Okay, so now let's get back to the fundamentals, right? Remember, like, let me ask you a simple question. So what is a good strategy to update the GPU drivers across, like, say, 100 nodes or 10,000 nodes in a Kubernetes cluster? All right. But traditionally, like, you may think of it like, in the microservice land, maybe, like, say, we need to upgrade kubelet, or maybe we need to like upgrade some daemon set, right? So we'd like to use progressive rollout, right? We first roll out like 1%, 5%, and gradually ramps up to 100%. And during each stage, we are going to, like, say, do a bunch of tests between them to make sure everything is fine, right? But on the GPU land, remember, like, some driver updates may interrupt your training job, right? So that means if you use this progressive rollout method, you may encounter multiple interruptions during your model trainings. This is quite that inefficient. So it turns out that if you can coordinate with your model training team or your AI practitioners and told them, okay, so let's just schedule a time for the maintenance, and you just stop the training, and we can perform the driver's update once for all, right? And that turns out to be more efficient. And that's the thing, like, I think traditionally we SREs think what's best for the production may not be the best for the in this type of situation, right? So other than that, we've discussed like how we can. My previous talk is all about like detecting degraded nodes and how to manage them, how to fix them. So is there anything else we can do, like any precautions we can do to proactively, right, to make things better? So we actually proposed for a proactive node benchmark protocol. So we have to run these type of benchmarks across different stages during our infrastructure management. So let's first see like what level of like benchmark test do we run these days. So the first level, we focus on the basic infrastructure tests, where we check if the pod can be actually scheduled on a single node, and if the node is fundamentally working correctly, right? And the second level is examine the GPU's basics, right? We test their like ECC errors or the XID errors from the hardware. Some hardware metrics exporters will export these metrics, and they can be very useful. And then we do performance testing to, like, say, computational focus. Maybe we use some load test to see, okay, if the GPU is working at a full, is fully working, right? And then next level, at level 4, we do multi-node testing, where we need to, like, say, select a bunch of nodes, test if they can communicate efficiently with each other, so that they can perform well in a distributed training strategy. And finally, we run several like actual models like small models trainings, run a few steps, and to see if all these nodes are getting prepared for the next training, right? So after we classify the level of benchmarks, we need to say, okay, so when do we run these benchmarks, right? Of course, we need to run them when the node is idle and nothing's on it, right? So there are 5 different stages we want to these benchmarks to be performed. So for the first one is during the pre-production validation, right? Before you actually accept this node in your Kubernetes clusters, right? You need to perform this type of benchmark. And before a very large model training, let's say the model training is predicted to last for 2 months. You actually want to perform this type of training, this type of test before that, so to guarantee that everything is working correctly. And of course, during the post-repair stage and during the fault diagnose stage, we need to run this type of benchmark so that we can quickly diagnose, make sure everything is working as we expected, right? And the actual architecture for such benchmark process is not that sexy. It's basically a cloud-native approach where you run a few operators and you design your own SREs to make things happen, right? You use your intent-driven design. You write a few benchmark CRDs for different GPUs, and you coordinate with your node-level operators so that they can select the correct node for you to perform the test, and you just recycle all those benchmark ports once you finish them. Okay. So to wrap up everything, so traditionally, for the cloud instance, you can see they are ephemeral and they are cheap, and they have low impact on the single point of failure, right? So we don't actually pay that much attention on the testing, and we just replace them. But on the GPU asset, they are kind of expensive, and they are persistent. They have large blast radius. So we need to do this type of extensive qualification and to babysit them to do the diagnose and repair. Okay, so finally, let's wrap up everything so that we can all go to lunch. So the key takeaways, if you would like to take a picture, this is a good slide. Today we first briefly talked about the characteristics of AI workload, right? And then we started rethinking about how we can do the reliability measurement. Is SLO still useful in this scenario? And then we picked 2 topics, one from observability and try to make friends with math and statistics. And then we do some GPU management methodology talk, right? Okay, so when we talk about the skill set, right, I think in the trend, previously we are all container-centric SREs, right? So we put container as the first hand, right? But I think sooner or later, everything is going to shift to model-centric. We are going to manage models. I think the 5 pillars for the SREs from the SRE book still works here. And it's not just about, well, in the traditional land, right, we have Kubernetes, we have Docker, we have Prometheus, Grafana, and some CI/CD tools. And we just need to make new friends with AI, right? We need to learn TensorFlow, we need to learn PyTorch. And the thing is, the most valuable skill for SREs is, I think, it's not about the specific tools. It's just our availability to transform ourselves alongside with a new infrastructure we manage, right? So before I ramp up to my final meme slide, I'd like to send a clap to acknowledge this work. Well, this presentation is a collective wisdom of my whole team, and it's thanks to my team for their pioneering work on the GPU observability and the management. And with that, that's my last slide, right? If you notice that I never talked about anything like agentic AI can help us in this land, because to me, I think we are pursuing deterministic universe, right? Even though that may not be 100% possible. But right now, agentic AI just makes things more like non-deterministic. So, but I think in the future, that may change, right? Because by the time I submit this talk, DeepSeek wasn't get any attention. And I think everything is evolving very fast. And for us, I think we just need to keep our mind open and try to learn everything new. And let's see, we hope like we can all get something new to talk about in the future, right? I'm happy to see if anyone can like say I'm wrong from this graph, right? I'm happy to see any agent that can help me solve my problem because everyone wants to make their life easier, right? Okay, so with that, I think I'll finish my talk here, and now I'm ready for the questions. Yeah.